Good morning. I'm Emad Benjamin. I'm a principal architect with VMware, and with me.
And I'm Jamie O'Mara. I'm a community engineer for Cloud Foundry for Pivotal.
A little bit about myself. I started out in the industry as a C++ engineer for a few years. Then in 95, 96, I switched over to programming with Java, and I've been on Java since then. And then in 2005, I started working with VMware, and this is where I started to move further down the stack and learn more about platforms and infrastructure. And then that created a full circle of everything that you'll hear about today and what I've written about.
And I'm Jamie O'Mara. So I'm with Pivotal. I started out as a software engineer, spent about 20 years doing software, and then made a transition to VMware in 2010, and then migrated back over to the SpringSource side in 2011 and have been there since. OK, just quickly, the agenda. We're going to talk about large scale. We're going to define what large scale is. I'll share with you the sort of problems I kind of solve for my customer base. We'll get into some sizing, then tuning. We'll actually do some GC tuning. Obviously not too extensive, but we will actually tune. And then we'll get into modern PaaS platforms, kind of applying all of the learnings from the many years of virtualizing and tuning JVMs to run applications in-house, to replicate that knowledge across to the PaaS, and then Q&A. Obviously, I take questions as we go through, so feel free to ask questions anytime. OK, so let's define what large-scale Java platforms are. Whenever I deal with a Java platform, I'm almost always dealing with these 4 technology tiers. There's a load balancer somewhere. There's a web server tier, a Java application server tier, and database server tier. Now, there are variants in the middle. Sometimes the web server is not there. Other times it is. Sometimes the Java application server is more than just an application server. It could be a messaging system and so on. But essentially, it's those 4 tiers. What complicates the discussion is that each one of those tiers is managed by a different team. And this is pretty consistent across many customers I talk to. You're already dealing with 4 different technology stacks, right, across the platform. But you're also dealing with 4 different teams that don't necessarily communicate with each other. And now you, as the platform engineer, has to kind of glue all of this together to make some sense out of it. Whether you're designing a new platform or troubleshooting, everyone's looking at you. Now, you may be a Java engineer who's dabbled a little bit with Linux and virtualization and a little bit with infrastructure. You may not have the full knowledge, but everyone's looking at you. You could also be a Java engineer that says, that's not my problem. Infrastructure is opaque. That's somebody else's problem. But you can only do that for so long before kind of circles back to you. And we're starting to see a lot of behavior change where developers will own features all the way to production. That's a trend that's pretty prominent out in the West Coast, where developers are incented to own features all the way into production. And it's forcing their skill set to change. And so let's talk a little bit about that, taking those 4 tiers and expanding them a little. Expanding the load balancer tier. First, we have some traffic that comes in, 1,000 hits, against the web server pool. So I have a web server pool, and I have a pool here of 4 web servers. We get what's called static transactions, right? Static page lookups, I should say, rather than transactions. These are all HTML lookups. The web servers will handle them and return back. Now, out of these 1,000, let's say 500 got handled by these 4 web server instances. That guides you to how much you actually need to size, right? Is it 2 web servers, 4, or 6? Knowing how many transactions or how many page hits you have to deal with will dictate the sizing of the Apache instances. And I've written quite a bit about this math that you can apply in terms of sizing HTTPD processes.
Now, the rest, the other 500, could be truly Java transactions. The web server sees and says, oh, it's got to go to Java, and it sends it to a secondary pool. Now, let me pause for a minute. What I see on customer sites is they miss the notion of a secondary pool. They actually just have one pool. It goes, the call goes into here, and if it's a dynamic call to Java, they hard code this web server to a particular Java application server. And this works okay for a little while until you get a JVM that crashes or it's in a 6 state. The load balancer doesn't see that because the load balancer will talk to the web server, and web server, I'm okay, I'm okay. So the load balancer continues to send traffic, yet it's all negative, right? It's not being fulfilled. So what we do instead is actually load balance that call again to the secondary pool, and then again we send out load balance to the instances of Java application servers. Again, the number of Java threads will dictate how big the heap will be, how many transactions you're doing, and then I'll show you math in terms of how to size these things. And then there's a relationship between the number of Java threads and the number of database connections. Ideally, it should be a step-down relationship. In other words, if you've got 100 concurrent Java threads, 10 database connections should work. But practically speaking, what I see out there, if you did do a step-down, you'll get a lot of deadlocks. A lot of Java applications are not written robustly to handle that. So you'll see almost a one-to-one relationship in some instances, which is ridiculous. 100 Java threads requiring 100 database connections. That's why you get this tension between DBAs and Java developers. But anyway, so as long as you're cognizant of the fact that it's excessive to be requesting that many database connections and eventually improve the code to have a step-down relationship, in the meantime, all you can do is just ask for more connections.
So are you
Yeah.
differentiating where Apache Mod JK fits in versus standard Apache? Just serving
No.
I'm trying to understand what you separated.
Separated what?
You've got something called a web server pool and an app server pool.
Yes. Let me repeat the question. Am I differentiating where Apache Mod JK fits in with the load balancer? So if I have a load balancer layer, I'd like to use my load balancer layer to do all of the load balancing. Because that way I control the entire scalability of my system in one layer. If I have to rely on something that does round robin or does something, right? That's not as robust and controllable, right? So I like to keep it in here. So Mod JK is not in here.
So that's a pretty big scale.
Yeah. Yeah, because you can configure, and you got web servers configured in here. I mean, it doesn't have to be Apache. It could be any web server, right? And then you basically configure all of the application servers in here. You load balance to this, and you send it out. The load balancer can do it. It does a good job. If you don't have a load balancer here, then yeah, you would consider other things. But who here doesn't have a load balancer on their application?
You've got Mod JK is dynamically, you can dynamically generate it.
Sure.
Production scheme, and you don't have to send those emails and change management meetings you were just talking about, right?
Yeah.
That's the whole advantage. I mean, that's Tomcat #1. Huge percentage are using Mod JK for the programmability and extensibility.
Yeah, if you're comfortable.
I understand that you're just saying in your ideal scenario you wouldn't use that.
Yeah, I wouldn't, because I wouldn't want to create a dependency. But if you're using it and you're happy with it, that's fine. But again, I think if you've already got a load balancer layer, why not actually use it? Yeah. But again, you would have to figure out, the sizing concept is still there. Whether it's another load balancer mechanism or not, it's still there. Okay, so in my humble opinion, who's a platform engineer? I think a platform engineer is somebody who is a developer or has been a developer, knows the notion of the JVM or the application runtime container, knows how to size that for different applications, and knows a little bit about the infrastructure and operating system, right? Putting all of those things together, they can, in an intelligent manner, size platforms. If you're a platform engineer, if you call yourself platform engineer and all you do all day, just write software
development and develop applications, and you know nothing about the other two segments, you really should not be calling yourself a platforms engineer. You're an application developer, you're a software engineer, right? That's what you should be calling yourself. Call yourself platform engineer, then you need to know about these two things. And knowing about these two things, it doesn't mean that every time you publish a service, that means it needs to go into one JVM, and quite kind of simplistically saying, you just spin out more JVMs as you spin out more services. That's not platform engineering either. There needs to be a mapping, there needs to be an understanding. We're going to get into it, and I'll show you later a little microservices implementation adjustment that I've had to do with a customer recently. Okay, so let's look at what these platforms look like. I like to categorize these platforms. First category, category 1, is web applications. So probably 80–90% of Java applications out there are web applications, right? They're getting some data from a database or some other data source. They're munging it, decorating it, and presenting it, right? And that's what most developers do all day, right? And if you look at these things, they tend to be hundreds and thousands, and the largest customer I had was 15,000 JVMs, okay, to make up their entire enterprise. When you try to look under the covers in terms of what's going on with the platform, category 1 tend to be CPU bound before they're actually memory bound. So let's take a step back. If you took a server that's about 256 gig worth of RAM on it, and it's got 2 sockets of 8 cores, so 16 cores, right, on it. If you wanted to completely consume up all of the RAM that's on there with 4 gig JVMs, you'd have to put 57 JVMs on that box, right? Now, in this instance, it's a virtualized box, so we have vSphere running on there. But regardless, 57 JVMs against 18 cores or 16 cores, you'll reach CPU contention before you know it. If all of those 57 GC cycles happen to, unfortunately, coincide, you're going to run out of CPU. And so the problem with category 1 type of platforms is CPU, not memory. So then what do you do? Well, either you buy 4-socket servers, get more cores and less memory, and balance that out that way, or consider consolidating some of the JVMs that are fragmented. They're just HA pairs of the same thing. Get rid of them, consolidate them, and move up in terms of heap space. So you can turn the dial kind of 2 ways. Category 2 type of platforms, there's only a handful of JVMs. You actually have to have a handful of JVMs, less than a dozen. It's in-memory databases, some very large messaging systems. And what we try to do is size one JVM within one VM that fits inside a Numa node within a socket. And I'm going to go into what that means. Recently, I've had to get involved in tuning an in-memory database for a customer. They wanted to put a 1 terabyte worth of data in memory, and they had sized it for about 30 JVMs. After really trying hard to get it to work, we ended up with 8 JVMs on 8 VMs on 4 physical hosts, well, ESX hosts with virtualization on it. 8 JVMs of about 90 gig heap space each, they got their performance. So big JVMs are not a bad thing, but they need to be applied to the appropriate workload, not for everything, right? And that doesn't mean you should let leaky code get away with it and give them more heap. Underlying code still needs to be fixed. So having these pictures in mind is really important because you want to know what kind of platform you're dealing with. And sometimes these platforms are mixed. And understanding that they're mixed and trying to design for their separation will give you, will just save you quite a few headaches. Oh, yeah, just wanted to. So basically with these ones, also, we often find 2-socket servers are the best. Because in-memory databases, very rarely are they CPU bound. They're much more memory bound. So as soon as you launch a JVM, you want to take all of the memory that's available on that Numa node immediately. Okay, and then we're starting to see this generational pattern of category 3, where category 1 applications use data from category 2. Now, this could be a messaging system, or could be an in-memory database, or like a combination, right? It's important to know how to size this platform versus that platform, right? The type of hardware and the type of sizing in this case is completely different to this. Here, you've got hundreds and thousands of JVMs. Here, you've only got a handful of JVMs, very big JVMs. Much smaller JVMs over here, much more physical hardware to virtualize here, much less hardware to virtualize there. So you're starting to, yeah, go ahead, question.
I was thinking about, like, does that really matter how many JVMs we have or how much memory? It's like all about how many threads hits to that JVM at one time, right? So even if you have 2 JVMs or 4 JVMs, if you have billions of threads hitting, you can kill that.
Let me,
So how do we balance
yeah.
in those?
Let me repeat the question. We're going to get into it in a minute. Actually, the question is, does it really matter the number of JVMs you have against cores? Isn't it really a matter of like how many threads are going through those JVMs? Is that fair? Yeah, I'd actually both matter, because you're right. You could have one JVM that's very busy, it's got 100 threads. Another JVM's got 2 threads. And those things do matter. But we'll get into sizing in a minute, and I'll show you how we do that. All right, so sizing. Let me just kind of animate this through. I like to take customers through these 3 steps. Basically, step 1 is working with them to understand the workload behavior. When is the peak of their workload? How many transactions do they get, right? You'd be surprised how many actually come back and say, well, development team is using a different monitoring tool, and infrastructure is using another monitoring tool, and I really don't know. And that's an honest answer, right? They don't know what it is. But if you don't know, then what kind of platform are we sizing? We're just guessing, right? And platform engineering is not guessing engineering, right? There's exactness to it. So I spend quite a bit of time. If there's no holistic monitoring system like vCenter operations or any of the other ones, I go to the load balancer and pull the load balancer stats out, because that tells me everything that came to that application through that single pane of glass, right, which is the load balancer. And I'll start there. Now, the load balancer stats may be too raw to consume, and you got to do a bunch of munging and so on, but eventually a proper monitoring system needs to be set up to collect all of that information. Once we've collected that information, identified, they have to handle 1,000 hits per second or whatever it is, then we do a vertical scalability and a scale-out test. This is pretty fundamental to every platform engineering, every Java application. If you don't do that, then again, you're just guessing it. And you can guess, and you can get pretty close, but most of the time, you're just paying too much for hardware that you're not utilizing. And then we create blueprints. And vSphere is pretty easy to create blueprints. So once you've sized up an entire cluster, you can save it and create other clusters based off of that. OK, but really what I wanted to focus on is step 2. Now, in step 2, what we do is set up a building block VM. We have, let's just make the math simple here. Now, earlier I talked about category 1 platforms, right? Category 1 platforms, you don't have to have a 1 JVM to 1 VM. You could have multiple JVMs on a VM. It's really to do with the number of JVMs to CPU ratio. In category 2 type of platforms, you really want to have 1 JVM per VM and consume up all of the CPU and all of the memory that's underneath that. But for this exercise, let's just assume a 1 JVM, 1 VM, so we can understand how it works. Let's say I put a 4 gig JVM here, 4 gig heap. I'm going to allocate half a gig to the off the heap section, and then half a gig for the OS. So entirely that VM is about 5 gig. We'll set reservation, which means physically allocate memory on startup to this VM and never take it away. So setting reservation is a pretty important feature for these type of applications, especially if you care about performance. I'll allocate 2 vCPUs to this, and then I exercise 100 concurrent threads. So when I look at my max thread setting, it'll be 100, for example. Then I certify this container to say it's 100 threads capable running a 4 gig heap with a total memory reservation of 5 gig. But my SLA says, you need 300 transactions, right? So I'm going to scale out exactly the same type of building block VM in order to fulfill those 300 transactions SLA. Now notice I'm using the exact same building block VM. These 3 VMs are actually configured into a load balancer pool. And the load balancer, you will use a least connection algorithm. Will send traffic in a round-robin fashion to the VM that has least number of connections. So it works perfectly. What I see out in the field is some customers will get into a bit of a troubleshooting problem on one of the VMs. It might need more CPU and so on. They'll bump this VM to 4 vCPUs. And then these are 2 vCPU and 2 vCPU, but fail to instruct the load balancer about that. And then they wonder why the traffic is not balanced. Well, the load balancer didn't know that you needed a weighted algorithm. I avoid getting into weighted algorithms. I like to keep them all the same. But if you get into weighted algorithms, you need to actually instruct the load balancer to do that. Let me just get over that. All right, so let's kind of dive a little bit deeper, right? Let's look at the memory structure. We have to understand the memory structure in order to be able to size it, right? Otherwise, what are we sizing for? So here I have a VM. I need some space for the operating system. And I need space for the Java process, okay? This brown box. Then I need, within the Java process, there's this section called the heap. Initial heap. The stack is within the Java process, but outside of the heap. The perm gen is, again, outside of the heap, but within the Java process, and other mem section. It turns out there's this section called off the heap section and the heap section, okay? So you'll find a lot of developers will tell you a lot about this section. And even with that, a lot of the minus XMX sizing is a guess. But nothing about off the heap section, right? And this is pretty critical. So VM memory is made up of guest OS memory plus JVM memory, and JVM memory is made up of the max heap, the perm gen, the number of concurrent threads times the stack, plus other mem section. And the stack for the Java, the Oracle Sun JVM, HotSpot JVM on Linux is 256K. Now in category 1 type of platforms, we don't really touch the stack, right? We leave it alone unless you've got bad reflection code and get stack overflow and we start tuning it. Well, we should fix the bad code, but that's essentially the situation where you get into that type of work. On category 2 in-memory databases, we actually tune the stack up because we want to crunch through as many transactions as possible within a single stack hit. Anyway, let's look at an actual sizing example. Here I have a 4 gig heap, and I'm going to set the initial heap to the max heap. You always want to do that if you care about performance, and you always want to do this and not bother about anything else. If you don't do it and get into the argument of, hey, I want to save some memory and so on, you will pay for it. Because if you don't set the initial heap equal to the max heap, let's say you set the initial heap to 2 gig, when you run out of the 2 gig and you have to actually repage, resize, you'll have to run a full GC, and that's going to cost you anyway. So commit the memory and go for it. Then I'm going to set, I'm going to model 100 threads. So I am modeling 100 threads here at 256K. 256 meg is for the application classes. And then other mem section here is about 3 to 5% of this number. Now, other mem section is where the JIT code sits, right? The code cache, the internal JVM information, send and receive socket communication, and direct buffer. So there are in-memory database products out there, not to pick on anybody, that use direct buffers, right? So they would be expanding this space. So it turns out your 4 gig heap is really not just 4 gig, it's 4.5. All right? So anytime someone tells you I need X amount of heap, they're really talking about 1.2 or 1.25x amount of memory that they're eventually going to need. And then I'll allocate, if it's Linux, I'll allocate half a gig. If you've got other things going on that operating system, you have to account for those. And then altogether, this is about 5 gig. This structure works for larger scales as well, as shown here. So for in-memory databases, here I'm showing a 30 gig heap. Kind of do the same thing. You'll notice here we've got a 1 meg stack. The largest stack I've worked with is 4 meg. And now, when you increase the stack size, you're essentially saying, I'm going to have fewer threads that I can run through. So you don't really care about that. All you're caring about is munging through the creation of the object graph as quickly as possible. So that's for in-memory databases. So, yeah.
You said we should set the initial memory size to the heap size.
Yeah.
So in what circumstances you suggest that we should set it to lesser memory?
Okay, so let me repeat the question for the camera. The questions poses that I'm recommending that you always set the initial heap to the max heap, and what instances you would set it not equal to the max heap, initial heap not equal to the max heap. I would always try and avoid not setting it equal to the max heap. The only time, and again, I'm cautioning against this because you're going to end up wasting a lot of time, is that let's say I've got a 360 gig heap, and I'm going to show you a monitoring system that was a 360 gig heap. Now, if I don't really have room for that bigger JVM, or I'm pretty close to the ceiling, I probably, in that instance, I would say, okay, let's set the initial to about 100, and let's leave the rest kind of variable. But you have to look at the workload, right? And so I would say the instances where dividends are paid for not setting the initial heap to the max heap are like in the 1 to 5% of incidents. So I avoid it. Yeah.
For Java 8, does the 1.5 still, I mean, PermGen isn't there, but I think they just shipped, right?
Okay, so the question is, for Java 8, is the PermGen still there or is it shifted? So the PermGen is actually not off the heap. They're dynamically managing it for you. You don't have to worry about it. You don't have to set it.
From a VM consumption perspective, you mentioned correctly there's a 1.2, 1.5. That will still be true, right? Because it's still
Yeah, but so the question is, I mentioned if you've got a heap X, then the total Java process is about 1.2, 1.25. Is that still true in Java 8? Absolutely. Absolutely, and I'm hoping it's not more than that with Java 8. We could talk later about an internal performance study that we're doing comparing 7 with 8. Anyhow, so then you're kind of faced with sizing in-memory databases, and someone is asking, well, how big can I have a VM? Like, what's guiding how big I can have in terms of these processes, right? There is a guidance, and the guidance is underneath the hood in what's called Numa architecture. So if you pick a server that's of 96 gig of RAM, that's 2-socket, and it's got 8 cores on each socket, total of 16 CPU cores, you could put 2 VMs on there of about 45 gig. And by the way, this applies to physical too. It's just that with VM, you've got Numa optimization that saves the day for you. But anyway, if you size the process or a VM that's, say, 48 gig, not all that. So basically, let me back up a bit. 96 gig worth of RAM approximately is half on this bank and half on that bank. It's not all contiguous in one place. It's split across the sockets, okay? So then if you size the process that's actually 48 gig, for that additional 2 to 3 gig, it has to go to the other socket and remotely fetch that memory to get it over to you. That's called Numa interleaving, borrowing from a neighboring socket. That's going to cost you about 30% drop in memory throughput. When you're sizing in-memory databases, or Java applications for that matter, that's a significant drop that you need to be aware of.
Will that show up on vCenter dashboards?
There's on ESX top, there's a flag called %L. Some of it will in terms of the Numa architecture and so on, but %L is actually, you could get that through the logs. and you could see it. And %L should be 100%. Otherwise, if it's not, that means you're interleaving. So sometimes we get into bake-offs where in-memory database is deployed on physical, and we deploy it on virtual, and it ends up actually working better on virtual. Reason is this Numa optimization. We actually have got every 20-second cycle, we calculate a Numa placement, a kind of an intelligent Numa placement in terms of where the processes should run for maximum local attachment to memory. On physical, there's no such notion. You have to use Numa CTL and control that yourself. Right? You can get it done, but you get it done today, and then tomorrow it's wrong anyway. Anyhow, so be aware of that. This will dictate how big of a process you can have. So you really cannot ignore the physical space. You can't ignore the infrastructure. And we go through these cycles in software development of like ignoring SQL, and then SQL comes back. I'm just an objects guy. Ignoring infrastructure, and then infrastructure comes back. We can only ignore the problem for so long. We're just shifting it somewhere else. Anyway, that was my rant for the day. So let me give you an equation that will give you how big of a VM process you need in order to be Numa local. So basically, this is the amount. This is the 96 gig that's on the host. That's 96 gig times the number of VMs, NVMs, as number of VMs. So if you've got a 2-socket box for in-memory databases, the best is 2 VMs, right? 1 VM per socket. 1 gig is the amount of memory required for vSphere, and then we divide it by number of sockets. That's how I got that 45 gig for the previous slide, for the VM size. And so if I size to that, this is the most performant configuration. Now, obviously, kind of that's the ceiling. If you don't want to go too close to the ceiling, you can just say, well, give me a 5% buffer on that number. And some customers will do that. If you're dealing with AMD, the Numa nodes are a half the size of the Intel, right? If you did the Intel calculation, you divide that by half, and then I'll give you basically the size on an AMD process. So it turns out that if I care about performance, really, I'm sizing a system for performance. It happens to be in-memory database. It could be a web application that I really care about. A 2-socket server has an NVMs of 2 as the perfect candidate. You can have more VMs, and it'll work, and it'll perform, but you're just paying a little bit more for managing that OS and doing other things, right? A 4-socket server, 4, and if it's AMD, just multiply these Intel numbers by 2. Because they stack up their Numa nodes. So our friends did some testing, and they chose a 2-socket server. So let's just focus on these 12 vCPUs. I've got a 2-socket server of 6 cores each. I have to decide how many VMs or how many vCPUs per VM is the best configuration. And so they did 6 VMs of 2 vCPU, 3 VMs of 4 vCPU, 2 VMs of 6 vCPU, and then 1 VM of 12 vCPU. And the clear winner was 2 VMs of 6 vCPU. That's because of the Numa perfect localization, right, and sizing. The next best was the 3 VMs. And the reason for that is because of our scheduling algorithm does a pretty good job every 20 seconds load balancing. Anyhow, so that's just some of the thinking you need to have at the back of your mind when you're sizing platforms, hence the notion of platform engineering. And here's an entire cluster of how this is. This is a typical, this is an in-memory database with big VMs on it, but you can use this cluster for category 1 if you wanted to. All you have to do is stack up multiple JVMs on here, right? In this case, I'm assuming 1 JVM, 1 VM if it's an in-memory database. If you deploy a web application on there instead of an in-memory database, and you should not mix the two, you can deploy multiple web containers in there. OK. So let's get into tuning. So with GC, From a virtualization perspective, we don't really care because we don't even know that actually Java is running on the virtual instance. But since we are in the business of platform engineering, our customers often say, well, I'm going to virtualize this application and I need it to perform, right? And can you give me anything, absolutely anything beyond virtualization that will better my application? And we say, absolutely. And this is where we get into a lot of GC tuning. You don't have to. It'll virtualize in place without having to change anything. But if you want to give it an extra boost, we can help. So it turns out GC tuning is a bit of a art versus science kind of mixed together. And if you look at GC policies, they're kind of either geared towards reducing the impact of latency or giving you better throughput, one at the cost of the other, okay? So big web applications will fall into that quadrant, right? Job schedules, batch mechanisms will fall into the other quadrant. They don't really care about response time. They care about pushing big objects through and more about memory throughput. And in-memory databases fall into this quadrant. Now, getting as close as possible to this line is nirvana. And I'll give you a configuration which gets you pretty close to that line where you don't have to worry about that. And we really have been testing that configuration across many workloads, and it works pretty good so far, surprisingly. But let's dig a little bit deeper here. So now I'm inside the heap, right? I'm taking you through a tour, a worldwide tour inside the memory. Eden space, survivor space 1, survivor space 2. We get minus XMN, which is the young generation. This is young generation. Now, I size the young generation about 33% of the heap size, not greater than 33%. The tuning range is somewhere between 15% and 33%. Pretty much consistent across a lot of things. Now, what happens, and so all generation will have the rest, right? There's no specific way that you can say, give me this much for all generation, right? It's just, if you size minus XMN, whatever is left is the difference between minus XMX and minus XMN, right? Minus XMX minus XMN gets you this area. Anyway, so Eden space, all objects are born in Eden. After some time, they die. We got a lot of minor GC, and what survives get copied to the first survivor space, the next survivor space, and so on. And in all of the tuning, this is the area that causes you the most trouble because it's milliseconds and seconds, things are happening fast, you don't have enough space to breathe, anything. So when you do tuning, you spend a lot of your time in here. All generation, there's a slower tenuership process or promotion process that actually copies across. Here, there's a card table reference type of copy, so it's fairly quick, but over here, it's a promotion. So it takes a while, a little bit longer comparatively speaking, to go to all generation. After some time, all generation fills up, and then a full GC, a slightly heavier process will come on board and clean things out, right? Let's just go back. I just want to make one statement about this. So actually, just recently, I was engaged in a product tuning, and the question to me was, well, how do you know how big the heap should be? You told me everything about all of the other sizes, but how do I know it's 4 gig, right? Why isn't it 2 gig? Why isn't it 10 gig? And so the trick to knowing that is this. After multiple full GCs, you run up the JVM, you run up the application workload, hit it with some pretty good, decent load, watch the thing run for an hour or whatever, watch full GCs go on for a little while. After 3, 4, 5 full GCs, you'll notice that there's a certain amount of memory never gets reclaimed. Now, hopefully that memory doesn't grow rapidly because you got a leak, but let's assume there's no leak. Goes down this way, goes down. That amount of memory is what we call surviving memory, active memory. That's not going to go away. That's the state, the data of your application. If that's X, your heap size is about 4X. Okay? So in this particular case that I was dealing with, that X was 12 gig, so that means they needed a minus XMX of 48 gig. pretty much, because think of it this way. That 12 gig that we talk about being active, it came from young generation, right? Now it's sitting in old generation. Now, you need some space to move 12 gig around, right? You need 12 gig space eventually, right, to move it around. As you're moving that around, another 12 gig supposedly is about to arrive, right? So you need space for that. So quickly you get into 3x to 4x type of space. So putting it all together, this kind of picture you should kind of post up on the wall somewhere and poke questions at it between your infrastructure admins and your Java developers and have them go at each other in terms of, nah, this is not true and so on, right? But if you get this right, you're on your way to improving your platform for Java applications. All right, let's get into some tuning. The most successful way of tuning these days, and including on Java 8 actually, and even better than some of the G1 numbers that we've seen, is to use a combination GC. In young generation, I use a par new GC, so it's kind of right there, and parallel GC threads. In old generation, I'll use concurrent mark and sweep. And what I'm doing is I'm going to be measuring the number of times this happens. It's the frequency of the GC, minor GC, and the duration. And duration is this, right? That's the duration of the pause. And I'll do the same thing in all generation. Now, this is significant because these gaps is when our application breathes and its threads run. When it hits this, nothing is running. So par new GC is parallel, but it still stops the world, right, when an actual thread runs. Now, it's made parallel by the fact they can have multiple parallel GC threads, and it's made a little bit more scalable. But when this runs, it still blocks. It still stops. Over here, it's not that bad. It's concurrent. It runs alongside your application threads. But this happens in a span of hours. This is happening in milliseconds and seconds, and you really don't have much space. So eliminating these things turns out to be a pretty good technique for improving the speed of your application. So this is what we're going to do. And also there's survivor spaces, right? There's two of them. I've done a lot of GC tuning for many, many years. And I went back through my notes, times that it was successful. And I ended up with a blueprint of what you can do to actually GC tune. So step one, or step A as I call it, like I said, measure the minor GC duration and frequency. Monitoring tools will give you this these days. And then adjust minus XMN and or adjust parallel GC threads. And I'll go through an exercise of adjusting minus XMN. Minus XMN is young generation. That's all you can do, these two kind of knobs. And then once you're done with that, you move on to old generation tuning. And all you can do there is adjust minus XMX. There's really nothing else you could do. And then survivor spaces. Now for web apps, for category 1 and 2, step A and step B, right? Including step C. For category 2, so in category 1, we never have to kind of touch the survivor spaces because survivor ratio of 8 is typically good enough. But in category 2 in in-memory databases, remember you're dealing with like a 90 gig space. Survivor spaces are probably, could be up to 5, 10 gig, right? So survivor spaces is a significant amount of space. So then we actually do tune survivor spaces there to take away some memory. Okay, so so we talked about measuring the duration and frequency. So let's actually apply it. So what is the impact? So here I have a situation. I have 3 minor GCs and I have 2 full GCs in all generation. I'm going to say that I need to get rid of one of these, right? Let's increase the young generation. Let's say I increase it by 10%. Anyway, what happens is when you increase young generation, you've created more space here. So that causes one frequency of minor GC to disappear. this is great. I've got a huge gap now. I can celebrate for today because tomorrow I got to figure out a different strategy. But anyway, so that's what happens. And then what is the impact of actually increasing young generation? Because there's always an impact to anything you do, right? There's a positive and a negative. The negative is that these two GCs that are left over, they're slightly wider. Not by a whole lot, but slightly wider. That means your pause, when it happens, is a little bit worse. But that doesn't matter because guess what? You just put 100 users, 100 more users through that gap. And so you average out okay. Now, because we increased minor GC, young generation, and we didn't adjust all generation, we took memory away from all generation. So all generation got squeezed out, right? And because got squeezed out, that means potentially a full GC might happen here. Now, one way of quickly fixing this, if I increase minus XMM by 10%, increase minus XMX by 10%, right? Another way of fixing it is, I don't care because this happens hours apart and I can afford it. In fact, these days with in-memory databases, we tune systems such that the heavy full GC doesn't happen till 12 hours after everything has, in terms of peak, has subsided. But if you wanted to mitigate it, you can. Now, how do you mitigate these pauses that have increased? Remember, these got a little bit wider. Well, it turns out if you've got plenty CPU cycles left on your operating system, you can increase the number of parallel GC threads. It'll help improve the scalability of young generation. Okay? That's essentially the steps I go through, kind of baby steps in terms of tuning. It's pretty tough to teach kind of tuning in an hour and a half. I have a workshop that I run. It takes 2 to 3 days. And yeah, I don't know what that is. It means I got to keep rolling. What about if you decrease young generation? What happens then? Decreasing young generation actually reduces the space and it causes more frequent minor GC. So why would you want to do that? Well, sometimes you might find that I've got a 100 gig JVM and young generation is really too big, right? And really most of my objects immediately go to the old generation. So I'm not doing much in young generation anyway. So I still, space away from young generation and give it to old generation. Now, when we do that, obviously we've increased the space. And if we've increased the space, the duration of the existing full GCs will go up. If you don't like that, you can decrease minus XMX, and so on. Survivor spaces. Well, survivor spaces are sized by survivor ratio. So if you increase this, survivor space size will go down. Now, I have a situation where everything's kind of pretty happy, right? But I've got a few too many of these. So what I'll do is I'll reduce survivor spaces by increasing survivor ratio. And now I've created a gap. Now more applications threads will run. Right? Now, again, the duration might increase a little bit, but I don't care about it. Got plenty CPU. I'm going to increase the parallel GC threads. What this does, the negative of it is, because survivor space is smaller, potentially I'll get more early tenuireship or promotion into old generation. And then as a result, because this was not adjusted, because minus XMX was not adjusted, then I might get an additional full GC. Right? But again, I may not care about that because this is hours apart and these are seconds and milliseconds. It turns out a lot of the combating is in here for web applications and some in-memory databases. I guess for everything is in here. But as soon as you fix this in web applications, this is rarely a problem. In in-memory databases, both of these are a problem. This old generation ends up being more of a problem. Okay, so here's a 50 gig example. Right? I have 50 gig initial heap and max. Young generation is 16 gig. I've got parallel GC threads of 6. This is a 12 vCPU VM. I allocated 50% of the CPU to the young generation because I want to give everything else some CPU cycles. as just summarizing what we did. Okay. All right. So using large pages. Now, some customers are shying away from using large pages. You know, you have to set large pages at the JVM level, at the OS level, and a bunch of other things that you have to do. And the problem is, you know, sizing large pages, you have to do 60% large pages, 40% small pages, because not everything can use large pages. So you do that 60-40 split today. Tomorrow, it may actually be wrong, because you may get other processes deployed in that operating system that need more large pages, and your 60-40 split ratio is wrong. So I tend to not worry about large pages anymore. Java does have a use Numa flag, but it's not compatible with CMS. So if you're virtualized, you don't have to worry about it, because you get the ESX vSphere Numa optimization. So you're lucky there. If you're on physical, you're going to have to do it by Numa CTL over here, which is not pretty. Here's a 30 gig example.
Go get somebody.
Yeah, we'll need to get somebody. It's just, it might be. All right, let's just keep rolling through this. Here I've got basically all of the flags defined. I won't read through them here. It's for your own consumption, your own reading. Okay, who's using WebSphere here? Okay, about 20%. All right. So everything I talked about was Sun JVM, right? WebSphere has the equivalent policies, and for a long time, the default was not GenCon, but now they've made GenCon as the default. And GenCon essentially is pretty similar to what I showed you, combination of PARN, UGC, and CMS, and it works pretty well. So always go on GenCon. And I've had an extensive conversation with some of IBM performance engineers about this. I'm really happy that they made GenCon default. It used to be this, and it wasn't great. All right. Let's kind of give you an actual example that happened out in the field. This particular customer had 25 unique REST services. They had dabbled with microservices thinking, and they designed this system where 25 REST services makes up their middleware services layer. And they decided one REST service sits on one JVM, right? And on day one, basically, they had 25 JVMs, 25 gig, and they rolled out. On day two, when they needed to scale out, they scaled out again, and again by 25, by 25, and they ended up with 400 JVMs across 16 physical hosts. And when I first actually engaged on this platform, and this is where the platform engineering hat comes on, I asked, what is the CPU utilization across your 16 physical hosts? And they said 15%. Immediately, I knew that they had a fragmented scale. What do I mean by that? They had overscaled out. And I said, what's your response time like? Well, our response time doesn't improve as we scale out. Boom, that's another problem. So after kind of playing around with it for a little while, I noticed that, wait a minute, your transactions, 90% of your transactions actually traverse all of your REST services. So why are your REST services all kind of fragmented out? Anyway, so let's hold that thought. So what happens, right? This is their load balancer layer. They got first call goes into first REST service, goes back to the load balancer, goes to a REST service. Now, if you're lucky, it goes to the same host. It's not that bad. If you're unlucky, it goes to another host, right? And you return the transaction. So there's this ping-ponging effect that's happening across their middleware, right? Across what's so-called microservices architecture, right? So what they proposed, they said, we don't want to change anything. So solution one, make it really easy. Instead of having 25 JVMs, we're going to put 50 JVMs and 2 VMs on this physical host. It's fine. You could do it. This is the cluster. You save on power. You get a smaller cluster instead of 16. But again, you really have not fixed the response time problem, right? Because even though you virtualize, the load balancer paradigm is still the same. right? Essentially. You still saved on power and so on. There was some saving, but your application is behaving as bad as it was before, right? And then they wanted to double the amount of traffic, right? So they were telling me, what happens when we double the amount of traffic? I said, you double the heap. You go by heap-based sizing. You have 400 gig heap today. You have to assume at least 800 gig of heap. So we sized the cluster this way and moved on, right? Using simple virtualization. Still, I wasn't really convinced that this was a done deal. So then I proposed, then I did some monitoring. I looked at, as I was saying earlier, 90% of your transactions traverse all your services. Why is that? Why is the 90% cases always remote, right? Shouldn't the 90% case be local and then the 10% case be remote? And you know, the Java architect there goes, well, this is microservices architecture. Well, microservices architecture should not mean fragmenting your scale. It should not mean that each service maps to one JVM, right? So instead of having 25 REST services, right, fragmented out, I took the 25 WAR files that they had, I deployed them on one JVM container, and then I scaled out, okay? So we ended up with larger JVMs, admittedly, right? And then basically their response time went improved by 3x, okay? Because what we had was the load balancer transaction would come in, we would load balance it to one of these JVMs, and it would actually stay in that JVM and go back. Because all of the 25 REST services are still deployed within one memory container. Now, they had 400 gig, right? 400 JVMs. So what I said was, okay, let me give you that 400 gig, but with 12 JVMs. So the cluster, the platform engineered cluster that was engineered by microservices thinking of 400 fragmented JVMs and a response time that was really bad, they're down to a system that's of 12 JVMs, right? And basically 3x better response time. But here's the other thing. They saved on 70% reduction in licensing of all those application server containers that they didn't need, right? So it turns out that you know, it's not really a good thing to always scale out. You have to know how to scale up versus scale out. And this is where true platform engineering comes into play. So we ended up getting into more discussions with the architect at the customer site. Is it working now? All right, I'll just keep rolling. So basically what happened was we ended up with these 12 big JVMs. The JVMs were like about 34 gig in heap size, right? About 12 of them. The architect challenged me saying, well, if a JVM crashes, you lose a lot more data, right? We used to lose 1 gig worth of data if a JVM crashes. Now we're going to lose 34 gig worth of data. And I said, you know what? You're absolutely right. You are going to lose more data. But I said, how is this situation worse than your old situation? And he goes, what do you mean? I go, well, let's look at a crash situation in your old paradigm. You had 400 JVMs. You had a soup of 25 REST services and many copies of them, right? JVM REST service number 23 goes down, right? JVM number 22 and number 24 and 25 don't really know about JVM 23 and REST service 23 just went down. They're up and running, but absolutely useless to be able to complete a transaction. Yes, you have these 25 JVMs up, but what are they doing? They're not completing your transactions. So in fact, it's worse because they're just sitting there consuming power and not doing anything for you. At this point, it was in total agreement, and you know, basically, I mean, we rolled out the system quite. And then, you know, the infrastructure guys loved it because they were dealing with a cluster of 400 JVMs down to like 12 JVMs to manage. Question over here.
I just wanted to ask, so the use case you mentioned, those 25 REST services really depended upon each other highly.
Yeah.
How does this problem change if those 25 REST services have no dependencies on each other?
Yeah.
What does your recommendation look like there?
Yeah. If they don't have any dependencies on each other, you can do whatever you want. You can scale out, you can scale up. Remember, as we go through, okay, so we did an experiment, and I'm jumping ahead through the content here. So there's a cost to scale up. Scale out is not free. Now, scale up is a little bit cheaper. So what we did, we tested out JVM. So we did a 4 gig, so we had a choice of 4 JVMs of 1 gig each, right? Versus 2 JVMs of 2 gig each, right? So net JVM heap is 4 gig. But one is 4 JVMs, one is 2 JVMs. Let me ask the audience, which is the better configuration? Who thinks 2 JVMs is a better configuration? Let's ignore the sockets now. Thank you. This is a great question, but let's just ignore that for a minute. Okay, about 10% think 2 JVMs. Who thinks the rest 4 JVMs? Yeah, actually the 2 JVMs was better, and here's why. It was 30% better response time and 60% less in CPU cycles. That's a significant reduction in infrastructure. Why? Because when you have 4 JVMs, you've got 2 additional GC cycles that you have to provision, 2 additional JVMs that you have to provision from an overhead perspective, that you don't have to do that over here. And so that, I'm not saying go run all your systems on 2 JVMs, but there's a cost to that scale up. We found the reason for that is the minute you bring up a JVM and it eats up that initial overhead, it can continue to vertically scale up without actually proportionally chewing up CPU cycles. So in other words, if I go from a 4 gig heap to an 8 gig heap, it doesn't mean I go from 2 CPUs to 4 CPUs. If that was the case, JVM vendors would be out of business, and JVM would not be scalable. The JVM is vertically scalable really, really well. Now, that doesn't mean go and turn every JVM into this big JVM, right? That's not what I'm saying. What I'm saying is, if you've got 15,000 JVMs of 1 gig each, and I have this with one customer, does that really make sense? And so, but anyway, but going back to your question, I mean, it doesn't, if the services are independent of each other, you're in total control as to what you do with that. I would still say, I would caution about fragmenting out too many instances. I would always ask the question, let's say I've got a REST service, it's doing well, and then all of a sudden I get a question, well, we'd like to scale it out. I'll ask, hey, should I just double the heap, or do you need another one? If you need another one, you need a new operating system, you need licensing for that, you need licensing for the new application container, and by the way, it's going to chew up more CPU. So tell me, why are you doing this? Is it a multi-tenant issue? Are you really truly trying to separate these things? If it is, then we'll pay for the cost. If it's not, then I'm just going to give you double the heap. And if I give you double the heap and your application doesn't benefit from that, you've got a scalability bottleneck issue within your application. Is that a question of, did I answer your question?
Yeah, I think so. And so the way you solve for multi-tenancy is just through, and deployment and bringing things in and out of service is just through HA?
I think so, yeah. And right now, the JVM is not multi-tenant. We are going to get into multi-tenant JVMs shortly. Shortly could be 1 or 2 years. But, and I promised myself not to get into that container discussion. It seems these days, if you say microservices or containers, immediately you got a buzz factor. But containers will play a role in multi-tenancy, but I believe JVM vendors will play a role in multi-tenant JVMs, and that's going to be very, very interesting for the container guys, because for Java workloads, there'll be kind of a choice, right? You could still have both together, but right now the JVM is not multi-tenant. And because the JVM is not multi-tenant, you're paying a significant price of spinning up additional JVMs to incorporate other tenants. Did we fix it?
Yeah, I think you're back up.
I'm back up. Did I do well, old school? All right. Let's get this question and we'll go back to, and come and see me afterwards. There is a longer answer I want to give you. Yeah, go ahead.
Maybe this is a longer answer as well, but I wanted to understand the idea of taking my E stack of 25 services, which is probably like one orchestrator and each
Yeah.
has 2 or 3 deep, something like that, 12 functions that are 2
Yeah.
deep, something like that. And part of the microservices goal there is to have independent scalability on all the different
Yeah.
tiers.
Yeah.
How do you gain the 3x performance by sticking on one? Is everyone a local
Yes. Yeah. So I didn't go through that. But you jumped through a few, like there were multiple questions in there. So you actually, that independence factor, so the question was, microservices talks about, flexibility and malleability of architecture. You can change a certain thing without causing brittle effect to everything else. That's actually not true. When you remove REST Service 23 instance number 5, it causes problems to everything else that's around it. What's good about the stacking of these services together in a containerized way, that the container is related to the transaction relationship of these things, is that when you actually take out that whole congruent whole, it just goes out. It's independent of everything else around it. The transactions that are within it are just transactions within it. They're not related to anybody else. Now, admittedly, it's an 80-20 rule. There's always going to be 1 or 2 transactions that'll leak out. Versus in the microservices soup world, the transactions is a graph, right? I mean, they're everywhere. So how do you take out this particular instance and update it without knowing how to trace the whole graph and say, look, I've impacted you guys? Now, they talk about application resiliency, and it doesn't really care. The notion of the pets and cattle and all of that. I'm actually currently writing about that because I think there's a lot of misconception in that area. You really cannot treat everything as a cattle, because when a cattle actually gets sick, look at it this way, right? First thing farmers do is they find out that cow needs to be quarantined, but who has that cow been in contact with? And they quarantine the whole thing. And so the same notion, I challenge to the guys who have been, freely talking about this on the blogosphere, is to think about that, is because you actually have to transcribe the transactional nature of those cows that interacted with each other and then put that in a container, because that's your transactional container. Anyway, this is like, I'm going off on a tangent here, but it is a question that, did I answer your question?
Yeah, you will.
And the other answer was, it is localhost. I did change it to localhost. Yes, I made it localhost. So you get the flexibility and you get the performance. I don't see a problem with it. And come see me afterwards, because, yeah, I know I'm causing a bit of a stir and thinking here, but I've been doing platform engineering for a very long time, and I know what works, and I'm happy to be corrected, but this works. And actually, it's interesting enough, Martin Fowler did come back and made an adjustment to his initial writing, and saying that maybe one microservice to one JVM is a little bit too far to the right, and maybe we need to reel that in. And essentially, that's what I'm saying. All right, so I think I kind of covered most of this. So this is basically the new paradigm is you basically have localhost transactions traversing in the same memory space versus the old way where it was fragmented. So I call it horizontal fragmentation. This is horizontal fragmentation of your microservices soup. What does it look like? Basically, this is what we're doing, right? It's all within the same heap. Here's the calculation, right? So basically, 12 JVMs on six hosts, virtualized hosts. And then for the following year, where they go 2x, 400 gig to 800 gig, is basically 24 JVMs. They were going to go to 800 JVMs. That's why you need platform engineering. You need platform engineering to tell you that I can get this done for you in 12 JVMs, and here is why. And this whole notion of ignoring infrastructure is like beneath you. It's not good. So here's the actual JVM size, stacking up everything together. Now notice, gentleman earlier asked about thread relationship. So in order to actually crunch through more and use up this heap space, I did increase the threads, basically, on the container. Here's a 360 gig JVM example. And basically, here, this was a vendor monitoring system that does not scale out, which is unfortunate. But I got engaged with them, And they had a physical box of 512 gig. We put virtualization on it. And this is the configuration. Where is parallel GC? Did that get cropped? Anyway, so basically, again, the same sort of thing followed through here. But what I did in this instance is after looking at the JVM and the way it was using things, no matter how you sized it on a 512 gig, 360 gig was going to be Numa wide. You always were interleaving. So I told this particular customer, you may benefit from actually going to a 200 gig JVM heap space. And they were like, really? I'll go, yeah, because then you fit inside one Numa node. And they actually ended up with a smaller JVM. So still pretty big. Again, increasing the heap is not always the answer. How are we doing on time? A small commercial pitch here. Obviously, VMware does have vCenter operations monitoring system. It's pretty cool in terms of being able to figure out trends of how your platform is behaving and give you hints as to what you need to scale up or scale out. The good thing is it uses Gemfire in the back end, which is why it's able to scale out. Versus some of the other monitoring systems don't necessarily scale out. And I think I switch over to you at this point. Oh, OK, so I talked through this. This, I walked through this. We did an actual test of 4 JVMs versus 2 JVMs, 4 1 gig JVMs versus 2 gig JVMs. Here it is. This is scenario 2, right there, the red. And this is actually response time. So as you can see, the response time was 26% better for the 2 JVM case. And the CPU utilization was about 60% less. All right. Any questions before I switch over to Jamie? And I think, what do we got, 10 minutes?
Until 10, yeah.
Sorry about that.
That's fine.
Yeah.
Just for clarification, is there a difference between using a 64-bit JVM versus 32-bit?
Yeah, the question is, just to clarify here, are we talking about 64-bit JVMs versus 32? We are talking about 64-bit JVMs. If I see a customer that has 32-bit, and I do see them, I encourage them to go to 64-bit. The unfortunate thing is I always say this, the 4 gig is the new 1 gig, because within the, if you take an application that's 1 gig worth of heap space that's running fine in 32-bit, and you move that across to 64-bit, your pointer doubles in size, right? So you actually may need 2 gig to run that. Now, JVM vendors knew that, and so they created compression, right? So -XX compressed ops is the flag. It'll automatically compress that down to 32-bit within the 64-bit JVM up to 4 gig. So 0 to 4 gig within 64-bit JVM, it automatically compresses to 32-bit. So you get the benefit of both worlds immediately. Now, between 4 to 32 gig, it's opportunistic compression. It'll still try and do it, but it's not there. Now, it goes up to 32 gig. Now, that doesn't mean in-memory databases, we only size up to 32 gig JVMs, because you saw that scenario. If I'm trying to host a 1 terabyte of in-memory database and I need 30 JVMs because, hey, I read somewhere that compression only applies to 32 gig, I don't care about that compression, because I have a different problem. We've got a latency problem due to the network. So I want to shrink that and go up in JVM heap size. So for web applications, 4 gig is the new norm, because that advantage. For in-memory databases, we don't care about compression. We try and size up as big a JVM as we can. So yes, we do assume. And the hangover is that, the customer that had 15,000 1 gig JVMs, it was a platform they designed and built in 32-bit days. They went to 64-bit and didn't change anything, right? I mean, it's like, look, you can run like 1,000, 2,000 JVMs or 5,000 JVMs. Anyhow, so that's that. Let me switch over to Jamie, and apologies for losing time.
So as Emad said, so this has been 5+ years for Emad kind of building this knowledge out and helping customers with this. And so you start to actually see a lot of what he's talking about in the platform engineering come through in Cloud Foundry. So the first, this is Cloud Foundry's architecture, which is the first thing you start to see is that dynamic routing layer up here, where he was talking about the load balancing and then accessing the different applications in the containers as they reside. So as you start to look at engineering a platform, you have to kind of handle what happens at the dynamic routing layer. Then you move into what he was talking about around containers, and that in the Cloud Foundry world is called the DEA, the Droplet Execution Agent. This is where your applications are going to start to live. So we want to take all of the knowledge that Emad's kind of gathered over the years and build this into our platform so that we offer these more as a service to the developers, so they're not having to actually they'll make determinations about which ones to use and how to use it, but it's actually offered to them as a service pre-packaged. And that's kind of the goal of what Cloud Foundry is designed to do. Plus we sprinkle in some additional pieces like health management of the applications, making sure that they're constantly up and available. And then logregation and aggregation of the logs for the application in the system, so that from an operator's perspective, they can always see what's going on. And from a developer's perspective, they still have visibility and insight to their applications. So in what I did with Emad is we worked on testing his theories out using Cloud Foundry. And what we did is we used the Spring Trader application and pushed it out to Cloud Foundry around the same tests that he was running with his the VMware approach on top of Cloud Foundry. So in our instance, Cloud Foundry was actually sitting on top of vSphere when we ran this. And so I'm going to show you a little demo real quick of this actually happening. But we took the Spring Trader application, which had the presentation layer here. We had our application RESTful services here. And then we had an integration service in the back end there. Where's the video?
It's here. Yeah.
Is it just slow to show?
Let's see.
So from an operator's perspective, this is what Cloud Foundry is going to look like to them. They're going to come in and they're going to go through the installation process. I'm not going to take you through all of the installation because I really want to show it to you from the developer's perspective. But they basically come in and do configuration of Cloud Foundry for the environment. So if in this case it was vSphere, it can be vCloud Director. In the future we'll do OpenStack, AWS, and Google Compute Engine. But really it's coming in and just providing the configuration for that environment and some of the networking that's needed to deploy Cloud Foundry. So Cloud Foundry deploys this like 25 virtual VMs, that reference architecture I showed you at the beginning. That's what Cloud Foundry looks like. Gets deployed into these VMs, and then the operations manager, which is what you're looking at here, actually manages the life cycle of the platform. So when it comes time to upgrade and patch, it goes through and recreates everything and moves your applications around as necessary to keep the platform up and running with zero downtime. Then in addition, this is where you start to add all the services. So you have the MySQL and the Rabbits. So from a developer's perspective, these are the services that they consume when they push their application. They can bind to it. So here's the developer console. And what we're going to do is we're going to actually take Spring Trader. We're going to create the services that we want to use for Spring Trader. So we're going to create a MySQL and a Rabbit. And then when we push our application, we're going to bind to these services as part of an auto-configuration capability. So here we're just creating the service. Now, if the application was already there, I could bind to it now, but I'm going to go ahead and push it in a minute, and you'll see that in action. Also, this marketplace that I'm showing you here, I only put 2 services in there, but there's probably about 10 other services that we offer. Plus, you can do external services too. So if you don't want Cloud Foundry to manage it, you have a production Oracle database, for example, you can provide that and link to it inside of here. So here's our services connected. And the next thing we're going to do is go ahead and actually push the Spring Trader application. So there's actually 3 applications get pushed. We create the route first, so that's what you see happening here. And then we start to upload the deployment artifacts. And as we go through that process, we're going to actually understand that we need to bind that to the services that we already created. And we're going to introspect that application to say, oh, well, we know exactly what this application needs to be able to be successful. This is where you'd start to use some of the things that Emad's put together in determining what some of the JVM settings are. So this detection here is called the build pack. This is where we make that determination about what we should run. So in this case, we figured out it was a war, so we're going to grab Tomcat, and we also grab the OpenJDK. But you could configure this for any type of application to use some of the best practices that Emad's had and built that into the platform. As part of this process, we'll try to start the instance of the application, so we'll see that start up here in just a second. And then for the others, I sped it up a little bit so we don't have to go through it, but this is going to do the same thing for the other two portions of the application. So we'll go through the detection again. Now we come back into the console, and when we go into our developer space, you'll actually see that now I have these three applications. You can tell the amount of memory that's associated to each one and the number of instances. So now what we want to do is be able to actually scale this up. So you'll see us scale it from 1 to 3. And all of this is why this is going, all this is actually taking load from your, currently from your customers or your end users. But you'll see that actually starting that up. And then the last piece that you'll see is that we've actually scaled it to 3. And now we're consuming, we've had that much more capacity to be able to handle the workload. So that's the end of the demonstration. But from what a lot of things that Emad's doing, we want to build that into Cloud Foundry. We want to make we're putting in features to make it so that you can push applications to certain places within the environment. A lot of that's based on some of the things that Emad's talked about.
Yeah, and a really good, and thank you, Jamie, and a really good PaaS platform should actually eventually dynamically calculate for you how many JVMs and basically the heap size and so on. We're not quite there in terms of that, but it's getting pretty close. Any questions that we haven't addressed? I know I got to talk to you because I need to give you the rest of the story. And the gentleman in the black shirt over there, come and see me afterwards. You won the book. You didn't know this. You were the first here and sat through the whole thing. That was the rule. Anyone else? Questions? Yeah, you want to ask a question now? Yeah.
Between, you mentioned large JVMs.
Yeah.
In the 30 gig-ish range. And
Yeah.
Small JVMs. What about stuff between 4 and 12-ish? That's
Yeah.
a very unknown space.
Yeah, it is a very unknown space. So I'll just talk through. So let me repeat the question. I talked about the super-sized 100 gig JVMs, 30 gig plus, and then the 4 gig. And the question is, what about in between? We get a lot in between customers. I get a lot of customers that have web applications that are sized at 6, 8, 12 gig. I've seen 25. It ends up being interesting based on the architecture that's internal to the web application, right? Some web applications are not architected well. You find the in-memory database is plugged into the web application, right? It's not separated out. So you can't really control this. I mean, we try to put boundaries around this method of thinking, but there's always cases where it doesn't fit. I think to answer your question, there's no problem. We can handle it. All that's in between, you can handle it. The JVM will vertically scale as much as possible. What limits you from vertically scaling up to provide more capacity is multi-tenancy. If somehow that's an application that's, if for you, it's, let's say, to go from 4 gig to 12 gig, it means that now you got to stop putting foreign applications from different tenants in there. They can't do that, right? It's not secure. You're going to impact multiple lines of businesses. So multi-tenancy stops you from doing that. When multi-tenant JVMs come around, you'll be able to do that. And the big JVMs will become the new norm. So I don't know if I answered your question, but yeah, they do exist. If I was back running a production system myself, I'd be looking to reduce the number of JVM instances. Because think of the monitoring agents that you got to install. Think of, 15,000 JVMs. I'm still talking to that customer. I'm trying to get them down to 3,000 JVMs if possible. But anyway. For that range? I wrote about this, I've written about this in the book. Sorry, don't mean to plug the book, but what's interesting right now with Java 7, with the PAR-new GC and CMS, I've tested that all throughout the range. In other words, you could apply my tunings right across the board. The only time that you got to be careful with that tuning is below the 2 vCPU range. So in other words, if you've got a 4 gig JVM heap that's sitting on a VM that's 2 vCPU, there's a flag called parallel GC threads. Remember, we set that to 50% of what's available. Well, 50% of 2 vCPU is 1 vCPU. You've just killed the tuning. You've made it serial. So what I suggest you do is you drop parallel GC threads altogether from the options and let the JVM actually calculate it. Now, the JVM will calculate it to 2, which is fine. Any other questions? Yeah, there's a question at the back, and then we'll come back here, and there's another one over there. Yeah, go ahead. Is there any way to download the slides? I believe we'll be uploading them
Yeah, I
somewhere.
think they're all available at the end.
If not,
I'm pretty sure they are.
yeah, reach out to me. I mean, ebenjamin@vmware.com or at vmjavabook on Twitter. Gentleman over here.
The question is about those RESTful services. The whole idea about deploying them into the distributed environment is that if one goes wrong, at least we have other to access it, so that we
Yeah.
better than that. So, but if we deploy it to just one JVM, all of those services, then
Okay.
it goes bad, then
Sure. Okay. So I think I'll repeat what you said, and I think there's a misunderstanding of the architecture here. The question is the goodness of the microservices architecture. You got massive scale out, plenty scale out. If one goes down, you got plenty copies there. Versus what I'm proposing, it's all in one silo and so on. If that goes down, then you're done. No, you're not done. That's not true. Because what happens is I've got 12 copies of those JVMs. For every REST service, I've got another 11 copies. So I do have plenty of scale up.
but if one service is dependent upon the other service, right? So, and they are deployed into the same JVM, that one service cannot go to the other JVM to access the same RESTful services. So then the main RESTful services.
Right. Okay. So I think your question is, what about retry logic, right? So what happens when a service, when you've got a vertical silo of 25 REST services, one of them goes down. Let's say this is REST service 23. 22 wants to escape and go somewhere else, right? Well, you've just had a JVM crash, right? That whole thing is going to go down. The retry logic should be on the burden of the caller, right? The caller, whether it's a client or something, should manage the retry logic, right? As soon as you retry, you shouldn't have the retry logic in here, right? And this is the problem of avoiding the graph of the soup of everything going anywhere. Remember, this is much more performant, and it's much more scalable, and it saves you a lot of money. Now you got to deal with putting the retry logic somewhere else where it really should belong. It's not a bad cost. But you're right, that is one aspect of it. I think I would be able to easily live with that aspect of it. Easily. You know, when your application doesn't perform, everybody hates it. When it performs really well, and sometimes you might have to recycle through a JVM. By the way, this is the myth, right? The myth is that if you stack up these JVMs, you've got a big JVM, if it crashes, it's really bad. You know, all your small JVMs, the 1 gig JVMs, they're absolutely useless because the young generation size of a 1 gig JVM is 300 meg at best. So really, you have a bunch of applications living inside 300 meg space. That's impacting your response time. They're bad 90% of the time. And by the way, the more number of JVMs you have, the highly likely that you will get a crash. So it's not all that bad. And there's a cost, right? There's 70% of licenses just gone. Okay, I'll give you another 24 JVMs. I'll give you 100 JVMs instead of 400. My architecture is still much better. All right. Question over here.
I have a related question. When you say the retry logic should be offered to a client or a calling party,
The caller. That's managing the transaction. Yeah.
if we design the microservices that we don't want to offer that, we usually deal it with inside. We define some services just for our own purposes. We don't want to expose or give the call
Yeah.
in that retry logic.
Sure. Okay.
What would be your suggestion?
You could do that. I mean, that's a code question. That's not really a platform engineering question. I mean, yeah, you could do that. And from a runtime perspective, to us, that doesn't really matter. You could absolutely do that. I mean, let me tell you my experience on retry logic, okay? If let's say you're running through a transaction, and then you call it once, and it's not there because there's a problem, what are the chances of you actually succeeding by retrying it 3 times, seconds after each other? Probably not very high, right? So most retry logic, and we're going to get into compensator patterns in here. I don't want to turn this into kind of distributed architecture discussion, but yeah, I mean, retry logic works for some things, but there's a cost to it. How many times are you going to retry? And maybe you should have a different architecture. Maybe you should offload that to a message bus somewhere to say, look, go and compensate. Things like that. So, and I think if you look at microservices architecture, they talk about stateless, right? I mean, everything just stateless. If something dies, dies, right? They don't try to recover. I mean, there's no whole notion of trying to recover from a transaction, mid-flight transaction. Nobody talks about that in any writing of microservices, right? Any other questions? No?
Right.
Okay. Thank you, guys. I really appreciated it. Sorry about the little glitch we had here. We'll follow up with the audio to correct. Otherwise, I hope this is what you expected.